In the first course of geometric crystallography, we have to study the crystal lattice, and particularly the axis, angle, and nodes, the reticular row, and the cell of two-dimensional lattice. We begin with the crystallographic axis and angle. To build a lattice, a crystallographic lattice, we must have three axes. The E-axis equivalent to the X-axis, the B-axis equivalent to the Y-axis, and the C-axis, which is equivalent to the Z-axis. The angle alpha is between the vector B and the vector C. Beta is between A and C, and gamma is between A and B. The three vectors A, B, and C are the basis vector of the lattice. We say also the crystallographic axis. A, the value of A, is the row parameter or the period of the row according to a direction, that is the direction of the x-axis. B is the row parameter or the period of the row according to the B direction, and the C is the row parameter or period according to C direction. Lattice of node, we have constructed here a lattice of nodes. We take the origin node here, and the other circle, black circle, are the other nodes of the lattice. We observe here that each basis vector starts from the origin, from O. Now we have to show the reticular row, and we begin with the definition. A reticular row is a straight line passing through two or more nodes of the lattice. It is designated by three indices, U, V, and W with capital letters, and U, V, W as three integers, three relative integers, which are in the set, in the mathematical set Z. And to calculate, firstly, I said also, or I said also that U, V, and W here must be coprime. To calculate the indices of a reticular row, we proceed as follows. First step, find two consecutive nodes on the row. Two consecutive nodes, the nodes which follow each other. Let us say the nodes N1 and N2. The second step, we have to determine the coordinates of the two nodes. Let's say the nodes N1 with coordinates U1, V1, W1, and the node N2 with the coordinates U2, V2, W2. Notice that the coordinates was written or are written with small letter. The third step, we calculate U, V, and W, such as U is equal to coordinates of the end node minus the coordinates of the origin or the origin node, U2 minus U1, V equals V2 minus V1, and W equals W2 minus W1. This is true if the row is traversed in the direction of N1 to N2 or N1 towards N2. If we change the direction of the row, if we traverse the row in the opposite direction or in the reverse direction, we calculate U, V, W as U equals U1 minus U2 2, V equals V1 minus V2, and W1 equals W1 minus W2. If we change the sense of traversing the row, we must interchange the coordinates. Now we have to do the calculation of or the determination of the indices of the reticular row. We have to take examples. We are going to draw a red row which passes through 3 nodes. This node here, this node here, and this node here. And this red row has as indices U1, V1, W1, and the green row which passes through this node and this node, and which has the indices as U2, V2, and W2. Now, to determine the indices of these reticular rows, we must determine the coordinates of each node on the row. If we want to determine the coordinates of this node, we have to do a translation which begin from O and arrive to this node. To go from this node from this node to this node, we have to do this translation: 1a plus 1b plus 1c, and we say that this node, called node P, has coordinate 1, 1, 1. In the same way, we can determine the nodes of the coordinates of this node, and we do the translation, which is equal to 2a plus 2b plus 2c, and we obtain the node Q with coordinates 2, 2, 2, 2a plus 2b plus 2c. In the same way, we have to determine the coordination of this node here. To determine the coordinate of this node here, we have to do the translation from O to this node. And the translation from O to this node is equals to 0a plus 1b plus 1c. And we say that this node, which is called node R, has as coordinates 0, 1, 1. And finally, we determine the coordinates of this node, which is called node S, and we find that to go from this node to this node, we have to do the translation 3a plus 0b plus 2c. And we say that this node, which is called S, has the coordinates 3, 0, 2, 3a plus 0b plus 2c. And now we can calculate the indices of the red reticular row and the green reticular row. We begin with the red reticular row, and we have to fix the origin node O0, 0, 0 and the end node P1, 1, 1. And as shown earlier, we calculate the indices with this way: U1 equals UP minus UO equals 1 minus 0 equals 1. V1 in the same way equals VP more VO equals 1 minus 0 equal 1, and W1 equals WP moins WO equals 1 minus 0 equals 1. And we say that this row, the red row, has as indices the indices U1, V1, W1 equal to 1, 1, 1. In the same way, we can choose the origin node as O coordinates 0, 0, 0 and end node Q with coordinates 2, 2, 2. And in the same way, we calculate U1 equals 2, V1 equals 2, and W1 equals 2. And we say that the red row has coordinates, has indices, has indices U1, V1, W1 equals 2, 2, 2 in within brackets. But these indices are not coprime because they have a greatest common divisor, which is 2. And if we divide this indices by 2, we obtain, as in the first case, U1 equals 1, V1 equals 1, and W1 equals 1. If we traverse the row in the opposite direction, in other words, with changing mutually the origin and the end, we take the origin as end and the end as origin, we find U1, V1, W1 equals minus 1, minus 1, minus 1, and we read 1 bar, 1 bar, 1 bar. And in the second case, U1 equals U1, V1, W1 equals 2 bar, 2 bar, 2 bar, minus 2, minus 2, minus 2. And if we go maintenant to the green row and take origin node at node R with coordinates 0, 1, 1, and the end node at S with coordinates 3, 0, 2, we obtain U2 equals 3, V2 equals minus 1, and W2 equals 1. And we say that U2, V2, W2 equals 3, 1 bar, 1. If the row is traversed in the opposite direction or in the reverse direction, we take as origin node S with coordinates 3, 0, 2 and end node R with coordinates 0, 1, 1. And we obtain U2 equals minus 3, V2 equals 1, and W2 equals minus 1. And we say that U2, V2, W2, the indices of the green row are 3 bar, 1, 1 bar. Now we finish with studying the cell of two-dimensional lattice. To construct the cell, we have to draw 4 nodes. The first node, second, third, and the fourth node. And we join this node to each other. And we find the cell of the two-dimensional lattice. With moving this cell to the right, we obtain a part of the lattice. And moving to the direction of vector B, we obtain another part of the lattice. And so on, we can build the lattice, the two-dimensional lattice. Here we draw with red color the single lattice which is occupied only on its vertices. The nodes are only on the vertices of this cell. Here we say that the multiplicity of the cell is equal to m equal 1. If we take as cell this blue cell, we have here the 4 vertices which are on the node, and one node here in the center of this cell. And here we say that we have a multiple cell, here we have a double cell, and the multiplicity is equal to 2. How to calculate the multiplicity? Take the lattice, the two-dimensional lattice, and draw the unit or the unit cell or the fundamental cell. We observe that on each vertices there is a quarter of the node which belong to this cell. Here we have a quarter of a node, a quarter of a node here, a quarter of a node here, and a quarter of a node here. That is, in this cell we have 4 quarters of node. Multiplicity equals 4 times 1 quarter equals 1. This is a single cell which have a multiplicity equals to 1. If we take the blue cell like this, yeah, we have also on the vertices, at each vertices we have a quarter of node like this, here, 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 and here. There are 4 quarters. That is 1 node to this cell, and we have here 1 node at the center which belongs totally to this cell, and the multiplicity finally is equal to 4 the vertices 4 times 1 quarter plus 1 times 1 to this node here, and we have a multiplicity equal to 2.